Look at this environment. Tropical reefs are highly studied ecosystems, bustling with angelfish, complex corals, and a dense, constant traffic of marine life. But if you follow the reef wall down to the ocean floor, the scenery changes. The activity stops, the terrain flattens out, and you are left staring at a blank, quiet expanse of warm sand. Then, in less than a 20th of a second, the sand breaks open. Scissor jaws erupt from the seabed, clamp down on a passing fish, and drag it beneath the surface at over 20 feet per second. Before the water even settles, the reef is quiet again. The animal responsible for that strike is Eunice aphroditois, commonly known as the bobbit worm. It is a segmented marine worm wrapped in iridescent armor, stretching nearly 3 meters long. Yet it operates entirely without eyes and lacks a true brain. How exactly does a blind, brainless invertebrate buried under the sand manage to calculate and execute one of the most precise, high-speed ambushes in the natural world? To understand the mechanism, we have to look underground. The worm spends its adult life coiled inside an L-shaped tunnel consisting of a deep vertical shaft and a horizontal living chamber. It builds this home by secreting a biological mucus that hardens into a permanent plaster wall. The only parts of the creature that ever reach the surface are 5 thin antennae arranged around its mouth. Since it cannot see, these structures act as an highly sensitive array of environmental sensors. This diagram illustrates how the worm senses its surroundings. The overlapping visual waves represent data the antennae collect. They taste chemical trails, feel microscopic pressure waves, and detect the sudden drop in light when a shadow passes overhead. The worm does not actively pursue its prey. It reads the water currents and waits. Once those pressure, chemical, and light inputs align perfectly to match the exact profile of a fish, a highly optimized physical sequence is triggered. The strike itself bypasses typical muscle contraction. The animal's body releases built-up mechanical tension, like a coiled spring snapping loose, thrusting the head upward through the sand. Leading that violent charge are the jaws. Structurally, they are built entirely from chitin, the exact same tough molecule that makes up the outer protective shells of insects. But this structural model highlights a profound biological adaptation. Rather than relying on pure chitin, the matrix is woven directly with heavy metals. Atoms of zinc and copper interlock completely with the organic protein. By infusing metal into the cutting edge, the blade approaches the hardness of human tooth enamel. When those jaws close, they have sheer force to cleanly sever a fish in half. If the physical impact doesn't immediately stop the prey, a secondary weapon takes over. The base of the jaw is hollow, delivering a faintly toxic venom straight into the wound that paralyzes the fish. Every anatomical feature serves a single, highly refined objective: neutralize the target's ability to resist, just long enough for the worm to drag it backward into the dark. To see how long this specific biological sequence has been operating, we look at the rocky coastlines of northeast Taiwan, specifically at layers of ancient seafloor deposited during the Miocene era, between 5 and 23 million years ago. In 2021, geologists working here discovered hundreds of strange vertical structures embedded in the rock. They were long, L-shaped stone tubes, which the researchers formally named Pennichnus. This cross-section compares the fossilized stone tube on the left with a modern bobbit worm burrow on the right. Notice how the geometries align perfectly. Combining this shape with distinct feather-like disturbance marks near the top and iron-ridged decay layers inside, scientists concluded these ancient tubes were the homes of giant marine ambush predators. The soft tissue, the jaws, and the mucus all rotted away millions of years ago. What the stone preserved is a trace fossil. It is a geological recording of an animal lunging from the sand, striking its prey, and retreating, repeated thousands of times until the earth itself held the shape. When we measure ancient biology, we usually think of extreme individual lifespans, like the towering trunks of old-growth redwoods that stand for thousands of years. But this worm represents an ancient lineage. 20 million years ago, the tectonic collisions that formed the Himalayas were still in their early stages. The highest mountains on Earth had not yet reached their peaks, but this marine predator was already fully formed and hunting. Today, it continues to act as a crucial ecological pressure. By picking off weak, slow, or sick fish, the worm filters the ecosystem, forcing the soft-bottom reef community to remain efficient and healthy. It is an evolutionary strategy that found its working form before modern continents even settled into place. Evolution built a tool that worked perfectly, and it has been waiting patiently beneath the